Students, welcome to Sunil's tutorial. I'm Sunil Mirwani and today we'll be doing this chapter called as EMI. Let's see what is the voltage magnification in an LCR circuit. Let's try to understand what is voltage magnification in an LCR circuit. Now, the effective value of the EMF, we've already done this, that is your RMS EMF. Effective value of EMF, E is equal to IR, where R is the resistance and the effective voltage drop across the inductor is going to be EL, which is going to be nothing but I into XL, right? XL we know is nothing but omega L, so this is going to be I omega L, right? Now, if I divide the two, that means if I divide voltage drop across L to the applied EMF, voltage drop across L, we said is omega I omega L. Applied EMF we know is nothing but IR. Thus, I can say this is nothing but omega L upon R, right? Omega is nothing but 2 pi F. So this is 2 pi FL upon R, right? Now, since for very high frequencies, at very high frequency, omega L upon R will be very high, because omega is 2 pi FL. If F is very high, that means omega L upon R will be very high. Right? Hence a voltage loop across L is quite high as compared to the EMF applied. If F becomes very high, see guys, in that case the effective voltage drop across the inductor will be very high as compared to the applied EMF. Hence, I can say that the voltage drop of a voltage loop across L is quite large as compared to the applied EMF, right? Hence, for a small EMF, potential difference across the inductor is appreciably high. Although I have applied only a small EMF, but the voltage drop across the inductor is very high. I can say hence, for a small EMF, the voltage drop across the inductor is appreciably high. Therefore, voltage magnification is obtained, although the applied voltage is small, but the potential drop across the inductor is high, which means that voltage magnification is obtained in an LCR circuit. Therefore, voltage magnification is obtained in an LCR circuit, right? Therefore, I can say that the magnification factor is going to be nothing but omega L upon R, which is also called the Q factor, right? Therefore, I can say that the voltage magnification factor Q, voltage magnification factor Q can be given by the formula omega L upon R, right? But for at resonance, we had found out that omega is equal to 1 upon root LC, right? Thus, I can say that the Q factor is 1 upon root LC into L by R, right? So in that case, I can say that this is going to be root of L upon C divided by R. So your magnification factor is going to be nothing but root of L upon C divided by R. Now, it is seen that the above condition in the series resonance circuit can produce voltage magnification. It is seen that the above condition in a series resonant circuit can produce voltage magnification. Right? So if I make Q as Q is root of L upon C divided by R, right? Voltage magnification, if the ratio of inductance to capacitance is very large, if I want voltage magnification in a resonance circuit, then the value of L upon C should be very high, right? First, the ratio of inductance to capacitance is very high. Inductance to capacitance is very high. Second, the value of R is very small. So these are the factors that produce voltage magnification, right? Now let's see the vector diagram for an LCR circuit. Vector diagram at resonance. Now, in the case of vector diagram, I can say that at resonance, XL is equal to XC. That is the condition required for resonance, right? Moreover, the effective voltage drop across inductor and across capacitor has to be equal and opposite in phase. Also, the effective voltage drop EL across inductor and effective voltage drop across capacitor, voltage drop EC across capacitor has to be same, are equal in magnitude and opposite in direction, equal in magnitude and opposite in direction, right? Hence I can say that the applied EMF is equal to the voltage drop across the resistance only. Therefore, since they are equal in magnitude and opposite in direction, that means the voltage drop across the inductor and the capacitor are going to cancel each other. The voltage drop across inductor is EL, across capacitor is EC. They are equal in magnitude, opposite in direction. That means they will cancel each other. Therefore, I can say that the applied EMF is equal to the voltage drop across the resistance only. So that means my vector diagram should be something like this. This is going to be my EC, this is EL, this is ER, and this is current, right? So at resonance, I can say that at resonance, first E will be equal to ER, right? The phase difference between E and I will be 0. Phase difference between E and I will be equal to 0, right? The impedance will be equal to minimum and it will be equal to R. Impedance is minimum and equal to R, and equal to the resistance. Fourth, since the impedance is minimum, obviously the current is maximum. Maximum current will flow through the circuit. The current is maximum, and though the applied EMF is very small, a high voltage can be obtained across L and C. Though the applied EMF is very small, a high voltage can be obtained across the LC, right? These are the things that would happen at resonance. Fine. Next, let's see an LCR circuit and in parallel. We saw a series LCR circuit. Now let us see a parallel LCR circuit. Inductor, capacitor. First, let's just see the inductor and the capacitor in parallel, applied across an EMF, an AC EMF, right? Let's assume I is the current flowing through the circuit, IC is the current flowing through the capacitance, IL is the current flowing through the inductor, L is the value of the inductor, C is the value of the capacitor, right? So you'll say consider an inductor L of negligible resistance because an inductor is a wire, so the wire is going to have resistance. So we are going to make sure that we take an inductor of negligible resistance connected in parallel to a capacitor C, right, and an alternating EMF, right? Now, in that case, the instantaneous EMF in the circuit will be E is equal to E0 sin omega t, right? Now we know that the current in the inductor lags behind the EMF by pi by 2 radians. The current in the inductor lags the EMF by pi by 2 radians. In the inductor we know that In the inductor, the EMF leads the current. Therefore, I can say that the instantaneous current I in the inductor IL will be equal to nothing but E0 upon XL, right? Ohm's law. Current is EMF upon resistance sine omega t minus pi by 2. Current lags the EMF, so therefore minus pi by 2. Right? Since it is instantaneous current, therefore sine omega t. Current by Ohm's law is E upon resistance. Instantaneous, therefore sine omega t. Lags, therefore minus pi by 2. Right? Now, sine, this is going to be nothing but sine minus pi by 2 plus omega t. Sine of minus theta is minus sine theta. So in that case, this will work out to minus E0 upon XL sine omega sine pi by 2 plus theta is nothing but cos theta, cos omega t. Therefore, the current in the inductor is going to be nothing but minus E0 upon XL cos omega t. Fine, do we get this thing clear? Next, let's find out the current in the capacitor. Now, I can say that the current in the capacitor leads the EMF. The current in the capacitor leads the EMF by pi by 2 radians, right? Hence, I can say that the instantaneous current in the capacitor IC current should be EMF upon resistance. So current is going to be EMF upon resistance. Since it is instantaneous, this is sine omega t. Since it lags, is going to be plus. No, it leads. Capacitance leads. So plus pi by 2. Right? The current leads the EMF, therefore plus pi by 2. In which case I can say sine pi by 2 plus theta is cos theta. So this is going to be E0 upon XC cos omega t. That will be my current in the capacitor. Now, by the diagram I can say that the current in the inductor and capacitor differ each other by a phase difference of pi radians, because in the capacitor it lags by pi by 2 radians. Sorry, in the inductor it lags by pi by 2 radians, in the capacitor it leads by pi by 2 radians. So the total phase difference between the two currents is going to be pi radians. I can say therefore currents IL and IC differ in phase by pi radians. Right? Therefore, I can say that the instantaneous current from the source, I is going to be nothing but IL plus IC. From the diagram it is very clear that I is going to be IL plus IC. So IL is nothing but minus E0 upon XL cos omega t plus E0 upon XC cos omega t, right? So in which case I can say that this is nothing but E0 common, 1 upon XC minus 1 upon XL cos omega t. Cos omega t is also common, right? But we know that XC is 1 upon omega c and XL is nothing but omega L. Therefore I can say that current I is E0 1 upon omega C minus omega L cos omega t. Right, denominator of denominator becomes numerator, not omega L, sorry, 1 upon omega L. So in that case this can be written as E0 is nothing but omega C minus 1 upon omega L cos omega t. That will be the instantaneous current. Now if omega C becomes equal to omega L, right? If omega C becomes equal to omega L, then I can say that there will be no current drawn from the source, because if omega C becomes equal to omega L, then the whole factor will become equal to 0, right? This and this will become equal, right? So I can say, instead of this, I'll write it this way. Omega L, if omega C becomes equal to 1 upon omega L, then no current is drawn from the source. No current is going to be drawn from the source, and this relationship is called as parallel resonance. This relation is called parallel resonance. Fine. So in which case I can say, therefore at resonance omega C is 1 upon omega L, right? But omega we had found out is 1 upon root LC, right? And omega is also equal to 2 pi f. Also omega is equal to 2 pi fr, where fr stands for resonance frequency. So in that case I can say fr is nothing but 2 pi upon omega, right? So fr is equal to 2 pi upon omega. Omega is root of LC. Wait, some mistake somewhere.
Omega upon 2 pi.
Yeah. Fr is going to be nothing but omega upon 2 pi. So Fr is going to be nothing but 1 upon 2 pi root LC. Fine. So I have my resonance frequency. So this is going to be your resonance in a parallel circuit. Right. So at resonance in a parallel circuit, no current is drawn from the source, and the resonance frequency can be found out by using the formula 1 upon 2 pi root of LC. This finishes the theory of this chapter. We'll stop this here for the day. Thank you very much.